but root with a real part and an imaginary part, and they will also come in conjugate. Okay, there will be, if you have a root a plus bi, you know that you have another root a minus bi. Okay, and then there's general form of the solution for the homogeneous part is this. So you have exponential at for the coming from the real part, and from the imaginary part you will have sine cosine bt sine bt, or you could have written both are equivalent. So you can write either in this form ibt negative ibt, or you do bt cosine and sine. Both are equivalent. But yeah.
For the cosine and sine part, are you writing the I as part of C2, or are you just
Correct.
Okay.
So it's absorbed in there, right? And so that's clear from here. Okay, and then after, once you know this, you don't have to go through the exercise every time. So either you write in the exponential form, or you just directly write in the sine and cosine form. Okay. And I'll start with a simple example, which also has biomedical applications, as I will see in the next lecture in the biomechanics. Remember, I wrote a bunch of application problems. One was the motion of the intervertebral disc, and that could be described by such an equation. And suppose I'm considering a mass spring system, a mass m, spring constant k, then second law of motion, mass times acceleration is total force. Okay. All of you have seen this in physics. And suppose x is the displacement. Spring force Fs. Do you know the form of the spring force if you stretch a spring? Kx. So it's, so if you stretch a spring by x and the spring constant is k, you feel a pull of negative kx. So the spring always tries to go to its natural position, natural length. Then the damping Fd is negative beta dx dt. And you could have an external force which is Ft. So suppose your spring is in some viscous medium. So always if you have a damping force, that's proportional to the velocity. That opposes the motion. So that's why it has a negative sign. And it's always, typically it's proportional to the velocity dx dt. Now if I could write this equation, everything is along this vertical direction. Okay? So we really don't have to keep track, don't have to write in vector form. Negative kx, negative beta dx dt plus Ft. Do you follow? So this is a general form of second order linear ODE. I can write d2x dt2 plus k over m x plus beta over m let me write this term first. Let me write the dx dt term first. So it's going to be beta over m dx dt plus k over m x equals ft. Now I can write this d2x dt2 plus, let me see the notation I used here, b dx dt plus cx ft. I'm dividing both sides of the equation by m, so make sure that you have the m here.
Wouldn't the terms on the left be over m squared now?
Which term are you talking about? From this step is fine. This d2x dt2. I am missing 2 here. dt2 plus beta over m dx dt plus k over mx equals ft over m. Looks okay to me.
Okay.
It's fine.
I see the change to B and C.
So b and c are constants. I put the constants into b and c. So b is beta over m and c is k over m. And if you look at the equation, it's a general form of second order linear ODE. Okay? And this is encountered, of course, in when you solve Newtonian motion, this is the equation, but you also encountered this in biology and like biomedical engineering. If you look into the handout, the first homework problem involves solving such an equation. Can you see that? The constants are a little different, okay? So I still have m with d2i dt2, so the constants are different there, but it's of the same form where ft is cosine, ft is cosine omega t. Yeah.
Just out of curiosity, is C equal K over M? Is K over M the frequency of the spring? Because I think I remember that.
That's the frequency of the spring.
Okay.
So you can, if you ignore this part, should I go to, yeah, let's go to the other board. First of all, you need to consider the homogeneous part to solve the equation. And if you ignore the damping, this is simply an equation of the spring motion. Okay? And do you know what's the type of solution to expect here? So if you solve this, suppose you do e to the power lambda t, you get lambda square plus c equals 0. So lambda is plus minus imaginary c. Are you with me? So what's the nature of this solution? Sine and cosine. So you get some c1 cosine ct plus c2 sine ct. It's a combination of sine and cosine. So it's oscillation. This motion is simply mass attached to a spring. So it's oscillating. That's the motion of that. Now you add the damping part. So the equation is changed. So you get, and the solution for such oscillations is going to look like that, if you remember. Okay. So remember, in the first order, differential equation, you got one time constant. You are never going to get such oscillation from a first order equation. You can get such oscillation from second order equation. Now, if I have the damping term, if I have B dx dt plus Cx equals 0, that's the homogeneous part you need to solve first. If I put e to the power lambda t, I get lambda square plus b lambda plus c equals 0. And the solution for this, if you remember, try e to the power lambda t. So that's the general answers. That's you always do. Whenever you encounter second order or third order linear ODE, you simply try e to the power lambda t, get the algebraic equation, solve that algebraic equation. So in this case, lambda is going to be negative b plus minus b square minus 4c by 2. Tell me if I'm wrong. Now, depending on the spring constant, depending on the mass of the system, spring constant, beta, you can have different types of solution. Okay? So if your base b square greater than 4c, what type of solution do you get? So you get both roots real. Both roots real. So the solution is x of t. So you will have, for example, a 2 time constant decay. This is from lambda 1 and this is from lambda 2. If you plot x of t. So you see that second order equation, you got 2 time constant in the system because you have a second order equation. For first order equation, if you remember, the exponential solution of cell growth problem, NT, or cell death, cell decay problem, you had only 1 time constant with 1k. Okay? So there could be 1 time constant in the problem. Because now you have a second order equation, you can have 2 time constant, lambda 1 and lambda 2. Then you can have the situation b square equals 4c, where both roots are equal. You have repeated root case, and then your xt is c1 plus c2t e to the power lambda t. Okay? If your both roots are repeated. And now you have a solution like this. And the third case, so this is 2, this is 1, and the third case where b square is less than 4c, then what type of solution do you expect? Sinusoidal. So if b square, look at the root, if b square is less than 4c, you are going to get an imaginary number. And as we discussed, imaginary numbers, they come in pairs. So the solution is